Hi, welcome back. Again, my name is Orlando, and in this video we're going to review Holt's method for exponential smoothing with a linear trend, and we're going to see how to implement it into R. So briefly to review, remember that the previous method that we discussed was the simple exponential smoothing, which was applicable for time series, for stationary series, so time series without a trend or seasonality. But now we're going to still consider a series without a seasonality component, but now with a trend, specifically a linear trend. So the idea now is to estimate both, for each period of time, to estimate both the level and the trend, and use both of those to make a forecast into the future. Okay? So we're going to have now two parameters, alpha and beta, and that's because, similar to the exponential smoothing method, where past data was intended to be less relevant than more recent data, the same is applicable here, but we have to estimate two things, the level and the trend, so it's convenient that both of those may have different smoothing constants, which we call alpha and beta. So one is for the level, one is for the trend. So the intercept is the level, and beta is the trend, which is the slope of the. So if you consider the time series to be more or less a linear function with some fluctuations, then the trend is really just the slope in this case. Okay. So since we need to estimate both the level and the trend, we need not only an initial estimate for the level, so an estimate of the level at time 0, we also need an estimate of the trend at time 0, so we need an initial trend as well. So we have four parameters: alpha, beta, L0, and T0. And by the way, it's recommended that we run a linear regression on the data that we have to estimate the initial level and trend. But much like before, that can create some bias because you're using all of the data and then making forecasts into that same data. So we're going to see an alternative method in a moment. So mathematically, the method is given like this. We need to, if we want to make a forecast, so if right now we are at time t and we want to make a forecast into the next period of time, then it makes sense that we go from our estimate of the level right now. So I mentioned here is a graph, and here is our current estimate of the level, and if we estimate that the trend is some value t, then it makes sense to estimate that in the next period of time, we are going to go from L to L plus T. So that's why the forecast into the immediate period of time is going to be just the sum of the estimates of the current level and the current trend. However, and this is unlike our previous methods where we did not have a trend, now because we are assuming a linear trend, if we want to forecast further into the future, let's say n periods of time into the future, then we need to add the trend multiple times. So our forecast into the future is not going to be a constant value, which again makes sense because if you're assuming that your time series has a linear trend, let's say increasing or declining, doesn't matter, but let's say increasing just to fix one, then I think it's very reasonable to guess that your forecast into the future should be increasing and not be sort of fixed, not stagnant. So if you assume now you're roughly at level L, then in the future you should increase whatever that L is by whatever you think the trend, the slope is, and that's for one period. And then for two periods, you need to sort of make two jumps So that's why you add twice the trend for a forecast twice, so 2 periods into the future, and in general for a forecast n periods into the future, you need to add n times the trend into your current estimate of the level. So these are the expressions. For the so this is for the exponential smoothing with a linear trend, but the Holt's methods specifically tells you how to compute, how to estimate the level and the trend. So this is where the Holt's method comes into place. It tells you, okay, so what we did before to estimate the level as a weighted sum of our data was a good idea. So as a weighted sum that sort of decays further into the past, that's a good idea. So let's sort of replicate that here, but let's do the same for both the level and the trend. So and to add extra flexibility, let's say that the smoothing constants for the level and the trend may not necessarily be the same. So let's give the level one constant alpha and another one beta for the trend, so they may be different. And so again, this is very similar as before. And now let's see how to implement this in R. So again, Professor Pazur gave you guys some R code to implement this using this function Holt-Winters. So let's load our data, again the same data kings. Let's transform it into a time series, a TS class. And now let's run this function Holt-Winters, which is so when you do not specify beta equals false, then it will assume you do want to use a linear trend. So that's the difference with our previous code. We had beta equals false, and now we do not have that, but we still have this gamma, which is related to another method we will see in the next video. And L_start is just the initial estimate for the level, and if we do not specify the initial estimate for the trend, then what this function will do is it will estimate the initial level. In this case, you're forcing it to be 60, which is just your first demand, and it will use as the initial estimate of the trend, it will use this quantity d2 minus d1, which makes sense. Is sort of a trend at the beginning, because the idea is not to use all of the data to avoid inducing bias into your forecasts. Because in practice, you would not have data into the future to estimate your trend right now. You will have to use data that you have now or past data. Okay, so we're going to run this, and well, much like before, you can easily retrieve the sum of square errors. You can retrieve the optimal value. So because we did not, so we removed beta, and we could, if we wanted, to force a specific value of beta and or alpha, but much like before, if you do not introduce alpha or beta, it's going to automatically compute alpha and beta, that the optimal values of alpha and beta that minimize the mean square error, the MSE. So if you inquire the value of alpha here, it's going to give you the optimal value of alpha, sort of the optimal value of alpha and together with beta, both of those together minimize the MSE. So beta is the same. So remember, both of these values are constants in 0 to 1. You can also inquire about the smoothed values. So this will be your L, and you can plot the results. And like before, you have your initial, your original data set and your smoothed version. Okay. Now we can also forecast much like before. Let's see, let's run this. So we're going to forecast 8 periods into the future, and let's see how it looks like. And now notice that forecasts are not constant. So there is going to be a trend into the future. And if you notice, it's actually decreasing. So that means our final estimate for the trend that must actually be negative. And we can actually figure out what that final estimate of the trend is. If we do this, so let's copy this guy, paste, then this is the final estimate of the trend. So this would be t at the length of the data set, so t42. So this is the final estimate of the trend, which is negative, and that explains why our forecasts into the future are decreasing. Okay, and like before, we have our lower and upper bounds for the different confidence intervals, so you can use that. And you can also plot the forecasts like before, and notice that so let's zoom in so it's easier to see. I don't want this. Why is it? I don't know why it's insisting on this plot. But anyway, so let's maybe zoom like this. No, it doesn't work. Okay, so I think it's clear enough from here that there is a linear decrease into our forecasts, which makes sense because we're assuming that this data set has a linear trend. Okay, and as you can see now, the width, let's say, of the confidence intervals is sort of increasing in a more, I'd say, more aggressive way. And there are reasons for that, but I will not go into it. Okay. Now, much like before, we can relatively easily implement manually our method, but to save you the work, I'm not going to go into the details. I'll just have the code here. You can analyze it if you'd like, but let's just quickly run it. So I'm assuming, so initially I'm going to fix alpha and beta as whatever the optimal values this Holt-Winters function was able to find. I'm just going to use those again. And the SSE or the MSE can be computed in this form. The SSE is this, and we can plot the results. As you can see, looks nice enough. And now let's find the optimal value of alpha and beta. And you're going to use a very similar procedure as in the previous video, except that because now the SSE can be seen as a function of alpha and beta, so we need to find the optimal value of alpha and beta. So SSE is going to be a function of two variables. So its plot is actually going to be in 3D, 3 dimensions. So using a graphical method to sort of informally optimize this function,